First of all, thanks everyone for attending. My name is Joel Hestness. I'm a research scientist at Baidu Research and our lab here in the Silicon Valley area. Today I'm going to talk to you about how your deep learning applications probably want scale and some ways that you can support it also. So some quick background for those that might not know much about Baidu. We are a search and advertising organization in China. Is one of the largest. We also are one of probably the most AI-focused organizations in China right now. And our deep learning research covers basically all of the major points that you hear about in a lot of these talks. So we have autonomous driving and robotics, object recognition, OCR systems, and digital personal assistants, which I work on and I'm going to tell you a bit about today. Overall, the organization and AI at Baidu has this focus on trying to hit seamless human interfaces, make everything work just great for the users. So to give you a preview of what I'm going to talk about today, I'll give an overview of some of the challenges that we run into in our conversational user interfaces. So that's speech recognition, speech generation, and the bits and pieces that fit in the middle. And I'll note that some of the challenges we run into there are just hard. We have to do a lot of engineering on the different models and things to get accuracy levels that we care about. And there's a special weapon that we've sort of discovered in the recent past, which is you can predictably improve accuracy by increasing data set size. And so I'm going to talk through a bunch of the details of what we found there and sort of convince you that you can use these weapons also. In particular, you can use these accurate predictions to kind of guess how much data you're going to need to improve accuracy to a level that you care about. And you can also start estimating the compute requirements that you'd have to get to that accuracy level for these with this data. And then I'm going to briefly reflect on something in our systems work that we found. All of this is going to require that we do large-scale parallelism, and I'll describe sort of the motivations there also. At Baidu, we're focusing on something like 10,000 times larger training scale than what you're seeing in the academic literature right now. And one of the challenges, we want to do that without waiting 100 years for a model to finish training. And that number comes from some detailed results that I have here. OK. So let me talk about our conversational user interfaces. Our conversational systems are aiming for a few different things. We want to be able to have very natural speech, natural interaction with the user, so they don't feel like it's something clunky. We want to be able to allow them to do very sophisticated queries. And so this comes in the form of sort of plugging in a bunch of services on the back to start with. But it's becoming more and more complicated than that. We have a lot of skills associated with our sort of smart speaker system, something like Google Home or Amazon Alexa. And we want to easily be able to plug in new capabilities in these systems. And so when I talk through this, we're aiming for very seamless interaction. So what does the system look like currently that we work on? It has three major components. So the first piece here is taking some input from the user. So it's a speech recognition system where we get sort of high dimensionality input, so in the form of speech, a waveform from the user. And we're going to reduce the dimensionality of that data down to something like text or annotations on that, something like pronunciation or other things. In the back end, we have language processing systems. I'll go into some of the detail on these, but these are deeply complicated things, and there are a lot of different potential applications and targets we can go at with these. I personally like working on these. And then speech generation on the other end. In the last year and a half or so, we've released three major revisions of our deep voice application, which takes sort of text or other annotations like pronunciation and projects them up to this high dimensional data again coming out, which is in the form of audio waveforms. So to go into some of the details on these systems, let's look at our speech recognition system. So this is a diagram of our Deep Speech 2 model. from a couple years ago. And something that we always found to be difficult with deep speech was trying to align text with the audio that's coming in on the input. So we had this system that was Alex Graves's dissertation, CTC loss function. It was difficult to get this to sort of train accurately. And so a bunch of researchers and our work looked through some of the current techniques in the area, things like attention and transducer models, and we did some comparisons there and have updated our models, and we have a couple of the papers that relay that information below here. In terms of the use case details of what we need to hit here, accuracy needs to be really good. We need we think we need a user to be angry with the system less than 1 out of 10 words that they state. It needs to be better than that. In fact, we try to measure it actually on the phrase level. If it's better than about 1 out of 5 in a full phrase that the user is unhappy, that's too much. The difficulties that we find when we're using the speech recognition systems, we see a lot of issues with environment. So there's noise in the environment. Things like riding in a car, the speech system is tough because you have a lot of ambient noise. And since I'm going to sort of reflect forward on the computational requirements of these systems, I'm going to mention what some of these networks have for compute requirements in kind of details about the model themselves. So here, the speech recognition systems we have numerous matrix operations, so they're heavy on linear algebra. These have some convolution, more convolution than some of the prior systems, and an attention mechanism. So these end up being very computationally intensive relative to some other bits and pieces that you'd use in some of these models. Let's go to the other end of this whole system, the speech generation side. This is our latest model, Deep Voice 3, and I'm going to highlight some of the things that make it hard to design a system like this. So the first thing is, and this is true for any speech generation system, when you're going up from a low-dimensional input like text to something like speech that's high-dimensional, you have to fill in all of that area with good, smoothed results. Otherwise, you get things like robotic voices. So there's been a lot of work just specifically on this to get good accuracy. We've incorporated some new things recently, speaker embedding that gives us some knobs to tune where we can change speaker characteristics. So we can change things like the pitch of the speaker, things like pronunciation and accents, so we can get interesting regional effects about the different speakers, and we can do this with very small amounts of training data. We can tune and adapt to different speakers. Finally, another thing that makes it challenging to do speech generation is the output projection. So you have this still sort of low-dimensional input coming into this thing that's going to project up to a waveform. Often you want to make sure that the speech coming out now is sort of dependent on the speech that you just generated before it. So you get these long-range dependencies trying to keep the audio smooth through time. And so you get dependencies, the different output mechanisms that we have, we've explored a bunch of them, and they tend to be pretty challenging on the compute side. Again, this contains a lot of linear algebra, a lot of convolution, and an attention mechanism in some cases here. So I won't go through much detail on our language processing stuff because we have a lot of different challenges that we try to tackle here. The big one for conversational interfaces is this dialogue idea. We want to make sure that when a user is interfacing with our device, they don't get stopped at some point. They don't run into something that keeps them from making forward progress. And so this means making sure we find the appropriate skills or actions that they want in response. Sometimes it also requires us to generate some knowledge or synthesize some knowledge from the input that they give. Here again, Lots of matrix operations, linear algebra, so these are computationally intensive. The one thing that I think is unique about these language systems, though, is most of them are very text-oriented, and so you have very low-dimensional inputs coming into these things, and you're generally generating low-dimensional outputs. And I'll explain why that's important when I get to our scaling results. Oops. Yeah, so in general, across all of these applications, improving accuracy is hard. The big thing here is that it's hard to improve accuracy by changing the models. So often that involves kind of rethinking these problems. So the weapon that I'm going to describe today is we can increase accuracy by increasing the amount of data that we use to train our models. And I'll show you how you can use this sort of approach to predict your data and compute requirements. So let me motivate this a little bit more. So what does it mean? What is the challenge with finding a new model? So often we get these libraries of models that we can throw at a problem. Sometimes even the library is not sufficient to give us good accuracy on certain problems. The talks that we've seen previously in this conference suggest that the theoreticians are the ones that are sort of reframing these problems. They're taking very complicated things with decades of experience in order to sort of reframe these problems and figure out how to improve accuracy. And the worst thing is, even if you can figure out how to reframe the problem, it's hard to get to predict the accuracy improvements that you're going to get. So prior studies have suggested that we can improve accuracy by increasing data. And I encourage you to think about what would it mean if you could predict the accuracy level that you could get from adding more data. So this is sort of a preview of the rest of the results that I'm going to describe. And this is what we call a learning curve. So it's distinguished from training curves or validation curves that you generally look at if you're training a particular model. So on the horizontal axis here, we have training data set size in log scale. So imagine increasing your training data set progressively here. On the vertical axis, you have generalization error. And so this is the error that you see on a test set or a validation set. The curves sort of start off with high error. And this is where you just don't have enough data to make any useful conclusions. At some point, you're going to tip over, and you'll start learning something from your data. And as you add more data, you're going to be able to learn more, and your error will go down. So on a log-log scale, I'm going to describe these as linear, and the slope of this is actually the exponent in the function I'm going to describe next. Eventually, if you have enough data, you can get down to irreducible error, but for all practical problems, I don't think you'll ever achieve that, so don't worry about it. So one thing that makes this pretty challenging, and as I go through this, you'll see it, you need to collect some of this data empirically to do these predictions. We're working on ways that you can do this, make these predictions without having to do this heavy empirical stuff. And finally, the slope of these curves actually defines sort of the difficulty of these different problems. And what we'll find is there's an interesting spread of difficulties of the different problems that I mentioned in our conversational systems. So before we dive into our results, let's take a quick step back and make sure we know what to expect from the results. So prior theory predicts that you should be able to get power law improvements in error, so reduction in error as you add data to your data sets. So the functions take this form. Error as a function of your data set size is some constant times the data set size in number of training samples to some power beta, and maybe plus a gamma. That might be that irreducible error we were talking about. In general, what I'll describe is that alpha and gamma are kind of uninteresting constants, uninteresting to those who are interested in the scaling factors, but they're very interesting to those that are refactoring these models to improve them. So I won't be focusing on these. I'll be focusing on that beta. And theory actually predicts that you should be able to achieve something like an upper bound or lower bound, I guess, of minus 0.5 on this scaling factor. So minus 0.5 would be the best case you could do. You'd be able to improve accuracy significantly as you add more data. These are called learning curves again, just to distinguish them from training curves or validation curves. All right, so here's our first set of results. What we did is we took a neural machine translation model. So it was a text-to-text encoder-decoder model with attention, something like the Luong attention paper, translating German to English speech from this data set. Basically, what we did is we sharded up the data size into chunks that were powers of 2 larger than the previous one. And we see sort of this predictable accuracy gain from 2 specific models. The blue line here has 208 hidden nodes, and the orange line has 512 hidden nodes. So these are different size models that are doing this training. The power law with a constant actually fits quite well in these cases. So because this is for a particular model, I want to note that as you increase the model size from 208 wide to 512 wide, you get this improvement in accuracy. The slope actually gets worse, which is strange. It's probably a residual from the curve fit. But the constant there is interesting, that the model runs out of capacity. It's going to have like a lower bound at a better score if it's a larger model. So that's actually a nice thing to see. That matches a lot of our intuition. Unfortunately, what we find even at this level is the exponent is not as good as that theoretical maximum or best that we could do, the slope minus 0.5. So let's look at this a little bit more practically. When you're training a model and you have a particular data set size, you're not going to train it with a particular model of particular size. You're going to scale up the model size if you have more data. You're going to find the best fit model given the data set size that you have. If you do that and start looking at the best fit model's score, and you're changing the model at each data set size, what you'll find is the slope of this curve changes even farther. We do see sort of a tail here. This follows this single power law without a constant very well. And what we found is actually with more sort of hyperparameter tuning and things, we can get this blue line to come down to the orange trend line. So it actually fits a power law without a constant, which is a little bit surprising. The big thing here is, though, that the slope is actually significantly worse. This is a flatter slope than that we showed previously, the minus 0.3. It's very poor compared to the theoretical predictions. So keep in mind that you would probably expect to see this, we think, with this preponderance of evidence that I'm about to show. So we reran this test on a bunch of different applications that we care about. So we tended to think that some of the models that were being trained in the academic literature that were getting a lot of attention seemed like sort of easy problems. Things like, to us, felt like easy problems. Image classification, even speech recognition, stuff that we cared to work on, seemed easy. We wanted to see if there was a difference with language, where machine translation has been a bunch of hard-fought wins over time. Language modeling is another one of these that seems like it moves along pretty slowly. So we tested the scaling here, and it turns out that the slope of these is actually very poor compared to, so this is like the hardest set of problems that we have. We find a slope of minus 0.06. Which is even, so the slope there is half as good as machine translation. What was interesting when we did this test was we tried a bunch of different models, different depths. They all showed this same curve. They all have the same asymptotic behavior, improving accuracy here. We also tested character language models, which have a slightly better slope. Now, character models have an even lower dimensional input than word language models, where you have the full vocabulary of words. Characters are something like order 100 if you consider all the different punctuation and things. They're slightly better. The interesting thing about this test was we also compared different optimizers in this case. So the top line here is an optimizer SGD, stochastic gradient descent. And we compared it against the atom optimizer, which gives us sort of a momentum term. The stochastic gradient descent does better, but it's a predictable amount better across the different data set sizes. And the slopes of these curves is almost indistinguishable. Some more evidence. So now we're getting more towards the speech recognition side, something that's sort of our bread and butter. We have a bunch of models laying around that we tested here, and I'm showing results for a couple of them. Now, one thing to note here is we didn't integrate a language model in this test, so it's maybe not exactly comparable to some of our published works, but the different models that we have here is our deep speech 2 model versus an attention model that we tested. The slopes of these are actually pretty similar, and they're significantly better than those language applications. So minus 0.3, it's pretty easy for us to improve accuracy with more data here. Finally, we tested image classification, and we looked at all of the different loss functions that you might consider as important when you're doing image classification. So cross entropy, top 1 error, top 5 error, every one of these behaved as the power law. Those obviously have different slopes, and it should be pretty clear why that is. So if I'm doing something like top 1 error versus top 5 error, if I have 5 guesses to make something right, I should be able to do better than just 1 guess. And so you kind of see the improvement in slope there. Now, the accuracy improvement here, the slope of this is closer to that theoretical improvement, but theoretical upper bound, but it's still not as good as we would hope. So to kind of recap, the power law region of these learning curves is really what matters. And what you'll find in practice is that they tend to be less steep than the theoretical numbers that are published. So the interesting things that I mentioned here is we've changed the models, we've changed the optimizers. They didn't really change the slope of these curves. The exponent here sort of indicates the difficulty of these problems, and I will describe what I mean specifically by that next. So we're interested in going from these sets of learning curves to projections about how does this affect our business? Can we use them to predict how we should operate as an organization? So a major factor there is we need to be able to scale up our training to larger things. So when we talk about larger data sets and larger models, I want to make sure that everyone kind of has a sense for the kinds of scale we're talking about. The community is already training on data sets that are something like order terabyte in size, specifically speech recognition. We have published that we have something like 10 terabyte speech recognition data set. And as you increase your data set size, you'd expect that your training time should grow roughly linearly in that data set size if you don't change any of the other factors. I still have to go through that data as many times as I did previously. So that's a factor that's working against us on scale. We also want to do larger models. So if you look at some of the publications from Google, for instance, their outrageously large neural networks paper, they want to try to train a model that's 1 trillion parameters. So for some perspective, compared to all the published results that we've seen, that would be about 300 times larger than anything that currently exists. So that seems sort of insane, but I'm here to tell you that it's probably not that insane. As we grow the models, we find that training step size probably grows roughly linearly in the model size also. We've got 2 factors probably working against us. As we grow the data set size, we get a slowdown in terms of training time. We need to grow the models also. So we probably get a slowdown on the model side also. But based on the projections that we have here, we could probably make predictions about how much compute is required. So just to give a sense for a case study before I get into our full set of results, If we looked at the word language model application, the current state-of-the-art perplexity is on the 4 gigabyte data set, the billion word data set. The perplexity level is about 29. And the projected perplexity that we think is important would be close to something like human-generated English language, so written, is something like 12 perplexity. So we're projecting that you need roughly about 100 times more data to get that accuracy improvement of about 2.4x. So let's talk about what that means along each of these applications. So here's that word language modeling. If the power law exponent here is not very good, we don't want a giant improvement. So this is improvement of cross entropy rather than perplexity. But 40% improvement requires about 100 times more data. That kind of sucks. That's pretty rough. The interesting thing about language modeling in some cases, so I'll put up character as another example here, even though these have poor power law exponents and they're going to require giant amounts of data, we get it's sort of easy for us to collect that data. Here we're just trying to predict the next word or character in a string, and we can just crawl the internet and collect a giant data set. So that's actually kind of nice. So even though we'd probably need 1,000 times more data to get to the accuracy we want with character models, we could probably just do that by pulling data from the internet. On the other hand, if you look at something like neural machine translation, here you have large data requirements. We want to get good accuracy improvements, a significant accuracy improvement. The trouble with with translation is we need to be able to relate sequences in one language to sequences in another. So this is in order to get this accuracy improvement, we have supervised or labeled training data. And to get those labels might be expensive. Speech recognition is also expensive on labeling. We don't need as much data there, but we actually project that the cost to get that accuracy improvement is still high. So there's a 20x difference with machine translation there, but it's still high cost to get that accuracy. And then image classification, the amount of scale that we'd want, there are probably public data sets that match this, although we'd probably want to go through and make sure that the labels are reasonably good. So something like ImageNet, in fact, some researchers have found that there are incorrect labels there. So this is an example of how we can project this to try to figure out accuracy cost. If I have some sense for how much each data element in my training set costs me. There's another factor to this which I want to go through, which is the difficulty to train at that scale. So now I have the data set, let's say. How much is it going to cost me to do the training? So word language models, say I have a 100x larger data set. So some of our work that I'll give you a link to at the end here suggests that we would need about a 23x larger model to train it on 100 times more data. So we'd expect that the training time, if everything else is equal, to be about 2,300 times longer. So that's pretty rough. But it gets worse on some of these harder problems. So character language models specifically, we need a model size that's gigantic, maybe 500 times larger than current. And so for some perspective, the amount of memory that is required there is probably more than one of our cluster high-performance clusters. Put in the rest here so you can see all of them. Machine translation is probably similar difficulty as character language modeling, but these language models are the ones that seem like they're going to be really hard to do. Because of the improved power law exponents of speech recognition and image classification, it looks like these are actually going to be easier problems to get to the scale that we'd like. So I'm going to give some more perspective here. If we tried to do this on our best cluster today, if we had enough memory, it would take about 200 years to train this model. To kind of back that out, if we went and projected Moore's law ahead 25 years or 30 years, that would get us to the scale where we could train this quickly. So we could wait for the hardware quicker than we could actually train from today's hardware. So that's a conclusion where it's kind of surprising what you can find with accurate predictions like this. So I want to talk about what it means to go beyond these bottlenecks. So these learning curves can help us predict the boundaries. We can kind of get to how much data we need for the next level of accuracy. We can estimate compute, memory, I/O requirements, et cetera. There are opportunities to reduce this difficulty significantly without kind of brute forcing it, without going to this giant system. So we've already seen the community shift towards algorithmic and optimization improvements. So optimizers with momentum, for instance, tend to converge faster, so we need fewer training steps. Algorithmically, we're switching to convolutional networks from fully connected networks that give us the opportunity to leverage these high throughput accelerators that are coming out, like the TPU. So another thing that our lab likes to work on is things like sparsity and low precision. So you've seen NVIDIA release their Volta GPU with mixed precision training, for instance. A lot of that was inspired by some of the work that we had done and collaborated with them on. So if we want to go without 10,000x larger on training scale without waiting 100 years to train, I'm going to make an argument that even with algorithmic changes, even with some of these optimization improvements, we're going to need more parallelism. And I want to give a brief tour of parallelism that we're thinking about. So parallelism is important, is probably more important than it's ever been in the past. First of all, Moore's law has helped us up to some point across the industries that need improvements in speed and computation. Usually those tasks, though, have been sort of linear tasks where the serial performance matters. They've stayed a bit away from very computationally expensive things, but now we're running into deep learning is something that's very computationally intensive compared to a lot of the prior applications for the industries that care about them. And in addition to the growth in compute requirements that we have for these applications, we're sort of seeing like the broadest discussion about things like deep learning that we've ever seen. We're seeing deep learning applied across many industries. It's touching applications across hundreds of millions, billions of users even. And so the compute requirements, if you take the user space, the industry space growth, and the compute requirements on a particular application together, it's a giant growth in the importance of parallelism. So let me give more detail about what that means. So some of you are aware of this. In training, we want to try to get low latency. Our metric internally at Baidu is how fast can we get a researcher to the new insight. Let's get them trained as quickly as possible. And so we're using GPUs and accelerators on these large-scale data problems. And they want results in less than hours. And this is basically impossible for the data sets we're talking about on a single GPU or even a few GPUs in some cases. On the flip side, for the consumer interested in inference, when we're trying to do inference at an edge device, local data analytics, we need to make sure that it's ultra low latency. They're not waiting forever to get a response. That's part of the seamless user interface. And we need to make sure that we're not burning up all of their battery life on a cell phone or something. So this means efficiently coordinating parallel work, smart caching of the data, keeping it local, things like that. So all of these challenges are about coordinating parallelism. And so I'm going to argue that you probably want to consider all the different possible forms at some level if you're thinking about the scale that we're thinking about. So brief overview of some of the aspects of parallelism that matter here. So the first one is kind of table stakes. Everybody that has a device needs to have kernels that operate at the full throughput of that device. So linear algebra kernels specifically exist for a CPU, a GPU, or every accelerator that's coming along. These are table stakes. You have to have these. Data parallelism, which I was sort of reflected on, splitting the data into chunks and training across multiple compute units, and then sharing the updates to your models. This currently gets us about 16 to 128x scale reliably. We can push this a bit farther if we really work at it, but it tends to be pretty difficult to do. And then for certain applications, there's a nice aspect, which is model parallelism. We can take the models that we have and divide the model itself across different compute devices and flow the data between them while we're doing computation on a different piece of data. And so we can get some good parallelism there, sometimes 2 to 10x. So be familiar with these if you're thinking about trying to get to this level of scale. So to conclude, I described sort of our conversational user interface challenges that we're aiming for seamless and natural interactions with humans. So you can go after this accuracy improvement by predicting, if you collect some data, you can predict how much data you should need to get to an accuracy level that you want. And you can begin estimating the compute requirements to do that also. And parallelism is going to be king. So special thanks. This is our paper that describes the scaling and also contains information about scaling models, which you might find interesting. And we have another paper on, turns out larger models actually train faster. And that's an interesting one. So thank you, and if I could take questions. Yeah.
You said a couple of times that when you have more data, you need a larger model.
Mm-hmm.
Can you explain the intuition? Because it's the same function, right, that's generating
Yes.
kind of approximate why you need a larger model.
Right. So the deal there is you could think of a smaller data set as something that lacks, so it doesn't have the full entropy of your full, like if you had all of the data, right? So as you grow the data set, you're going to find more bits of nuance that you could try to pull out of that data. So a larger model is going to give you more capacity to try to remember that nuance, those little bits and pieces that get you good generalization on small things. So you have to probably try a wider model or a deeper model depending on the application. Mm-hmm. Yes?
Between the data parallelism and the model one, doing like splitting the model only give you like 2 or 10 times as much. Why do you want to do that instead of like, I mean, like in which case you choose model over like data?
That's a good question. So I mentioned both training and inference. So the question is, when would you choose data parallelism over model parallelism? So I would argue that in the training scenario, you're always going to want to try to use data parallelism to start with. And depending on the scale you want to get to, that may or may not get you reasonable training time. So that's something worth considering. You might end up going over to model parallelism in order to get the full scale that you need. Sorry?
You mean like with both with training?
Yes, you can do both, yeah. So we're looking at, if we wanted to get to 10,000x scale on a word language model, we've projected forward, we would need both to do that. And we'd need about 2,000 GPUs to train at this 100x larger scale. And for perspective, it would take about a week to do an epoch through that data, which is a lot. On the flip side, I mentioned inference also. When you're doing inference in certain deployment scenarios, like if you have a request coming into your data center where you want to respond with some sophisticated answer like a search ranking or something, you might also want to shard up your data or shard up your model across different compute units to get parallelism through the model. So you can have multiple different queries going through it concurrently. So we have to consider all of these, is sort of the argument I'm making. Mm-hmm. Yeah.
Could you show the slide again that compares SGD's curve versus Adam's curve?
Yes. This guy.
Right. It seems like the Adam is doing better since it has a smaller loss and also a smaller
Yes.
SGD is better. I'm not sure if.
So it's probably hard to tease this apart. So some of these tests involved, heavy-duty hyperparameter tuning. This one I can't recall, but we also had trouble training on the larger data sets, so take it with a grain of salt. But the improvement that you see on the constant is sort of a constant factor. It's about 6%, regardless of the data set size that you use. The difference between SGD and Atom that we found that was important is we actually ended up using a much larger model with SGD in order to get better accuracy. So it's probably the case that model was doing something like memorizing some of the training set and things. So there's probably a bunch of factors here that might be hard to read into. So we were really focused on trying to measure the slope of these curves. Yeah. All right. Well, thanks again.